I remember when I was in 9th grade and we had to do these formal geometric proofs, I thought they were boring, to say the least, right? It's a long process of giving statements and then reasons, and a lot of it seems sort of counterintuitive or wasteful or like busy work, because sometimes, well, it just seems obvious what an answer is, and then other times there are different methods that we could use to solve some of these types of problems. Like we could measure, for example, we can measure angles, we have tools, and certainly with our technology these days, there are plenty of other ways that we could possibly avoid doing these double column proofs, but as a standard in education, if you go through a course of mathematics classes, you'll encounter these. And in the scope of broader scientific and mathematical education, I'd like to rephrase these or present these as a way, as part of a larger archetype, where we are not just getting straight to the answer, we're not leaving any room for doubt, right? A proof a long, long time ago was exactly what it sounds like, proof. So it removes all doubt. And by giving the statements and the reasons each step of the way, even if it's tedious and even if it seems like, well, why should we have to prove something that's just so obvious and transparent? Because it removes that doubt. And in the scientific process, if we are making hypotheses and then trying to draw conclusions from those, perhaps leading to theorems, like we'll see in a moment, many different people spent their whole lives proving things that were, again, true on the face of it, and they could have just said, well, this is true, but to remove all doubt and to phrase the proof in a manner of logical thinking, well, these actually have a lot of value that we could apply in different areas of our lives too. So with the view of looking at this process as having broader value, again, in making a statement and then having some proof, and then going to another statement and then having some proof each logical step of the way, showing our work, not just because it's required on a test or because it's outdated or old-fashioned, but because it shows to other people who might not be able to make that inferential jump from one step to the next, what exactly we're using to justify our next and final statements in a causal or logical chain. And so in this first example, we have given that AEB, this triangle here, is congruent to DEC, this triangle here, and also that AE is congruent to ED, right? So this this angle here, AEB and DEC is congruent. These two are congruent, and then these segments here are congruent. So we can see that we have a larger isosceles triangle. We want to prove that AEB is congruent to triangle DEC. These two outside triangles are congruent. And so, well, again, we could take out our rulers and our protractors and measure. There are other ways that we could do this. We could just plug it into a computer, or we could close the geometry book and say, well, this is boring, and why should I have to do this? But again, in sciences, as we move through the different more elementary levels, then a lot of our other sciences are grounded in math, and so math follows and then leads to that sort of logical thinking, that process where we're making statements and then giving reasons so that other people who are unrelated to or have little knowledge of exactly what we're working on can look at that logical chain and then come to the same conclusion, which is ideally what we have in science, right? Where we can take one person's results, give it to other people, and they can independently verify those results, rather than a system more like philosophy or religion where we're sort of faith-based. We can't prove necessarily several different aspects. And that's one of the strengths of the sciences, is that we can independently verify assumptions or conclusions, right? So we know from the given data here, from the given information, that these two angles and these two segments are congruent or equal. And so then, using postulates and theorems that people spent years and years and years developing, we can come to this conclusion. Firstly, let's look at angle A. This angle here is congruent to this angle here. And if these two sides are equal, we know this is an isosceles triangle. And so the two sides of a triangle are congruent here and here. Then the angles opposite here and here are also congruent. We know that the base angles of an isosceles triangle are congruent also. We could phrase that differently. Finally, step 4, we know that AEB, this triangle, is congruent to this triangle because if we have an angle and a side, then we also know that we have angle, side, angle. So if we've got this angle, this side, and this angle, then we've got angle, side, angle, which means we can show without a doubt that these two are congruent by the ASA principle. Okay, next one. Again, just getting into the habit of kind of drawing out our logic, right? And slowing down the process, not only so that we know ourselves that there are justifiable reasons, but also so that we can present these things to other people and have a step-by-step process that we can show them how we came to a conclusion. So this might seem like a trivial sort of example, but at those elementary levels, building upon skills, this is the type of knowledge of processes and knowledge of logical thinking that we're going to use later on. And so, again, it might seem arbitrary that we're writing out these long proofs with triangles, but in fact, it has value not only in mathematics, but later in sciences and even in life. So given, we've got AB, this segment here is congruent or equal to DE here, and then we know these two are also parallel. AB and DE are parallel. We know that AC, this segment here from A to C, is congruent to DF here. And we want to prove that BC is parallel to FE. So we're going to start with our given. Always start with at least one given. Right, and so then we also know that A and D are equal or congruent because they are alternate interior angles. We have parallel lines here, and we know that if we have a transversal cutting those two parallel lines, then the alternate interior angles are congruent or equal. And we've got another given here, AC equals DF. So then we know that triangle BAC is congruent to EDF because of side, angle, side. We've got angles here, we were given a side, and we're given a side here, so all we had to do is prove that the angle between these two sides, the angles were congruent, and then we can prove those two triangles are congruent. Next, angle BAC, BCA, this angle here, is congruent to this angle here, because corresponding parts of congruent triangles are also congruent. And so we could work backwards, or then it is intuitive that we've got alternate interior angles here, right? Two lines. If these two angles are equal, and this is just one line, then we know these two are parallel because alternate interior angles. And so we've got these two triangles are congruent. These two angles are then the same. These sides share a line segment. These two are parallel. These two angles are equal by the same principle that these two angles are equal, or congruent, because parallel lines cut by transversal have alternate interior angles that are congruent. And so, next one, again, I understand perfectly well, and I think most people who've done these understand that it seems tedious, and at some point we're all like, well, why are we doing this? Whether it's geometry or whether it's showing our work on a long math problem, why can't we just use our calculator, use the technology? It makes perfect sense. That's what a lot of people are doing in the real world, especially with problems that are not necessarily related to the real world. However, we're developing skills of logical thinking and presenting statements and giving reasons in a logical chain, which has broader application. And so slowing ourselves down and being able to logically think about why we know something, and then have that lead to another statement with a reason on down to a final conclusion is a very important process to understand. And it does take a lot of practice and a lot of time to develop these core skills which can sort of structure the brain such that even in areas outside of what we might traditionally think of as science, we can apply these types of skills. So here we've got a triangle, we've got a couple of rays shooting off here. We know that YZ is the base of an isosceles triangle, so we know that YX and XZ then are equal, right? We want to prove, we also know that XA, the point here, XA is congruent to they're parallel, YZ. And we want to prove that angle 1 and angle 2 are equal. Well, this one's pretty simple, I think. These two are corresponding angles or alternate interior angles. Well, they're not alternate interior, they are vertical angles. No, they are corresponding angles. Anyway, we'll get to it. Angle Y and angle Z are congruent because they are the base angles of an isosceles triangle. XA and YZ, that's a given. And we know that angle 1 and angle Y are equal because two lines cut by transversal if they have corresponding angles. Right, so memorizing the terminology is one part of the puzzle. But even if you don't know the particular name, that's more of like a linguistic or language type of intelligence, you can still understand the concept that those two angles are equal. Right, and finally, angle 2, looking at angle 2 now is, right, these are the opposite interior angles, alternate interior angles, we know they're equal. And so finally, we know that angle 1 and angle 2 are equal because, well, if these two are equal and these two are equal, by the transitive property of congruence, then we know that these two are equal. In our final example, we've got a trapezoid here. Looks like a regular trapezoid where segment AB, the two legs here, are congruent, and then the two base angles are congruent. Then we know that if these two line segments are cutting those vertices, then this is an isosceles triangle. We want to prove that. We know that already, but we want to prove it again. We should know it intuitively if we know a lot about geometry, but in order to prove that, we want to go through those formal logical chains, which again are important for providing reasons, making sure that we don't come to improper conclusions in more or less elementary or simple geometry, but they also give us that groundwork, that basis for other logical thinking and this type of mental reasoning, right, that we're going to use in later science and math, and also out in debate, ideally, and appropriately politics and law. We should always have reasons. I mean, even in giving an opinion, we should have some reasons and then be able to link those to prior assumptions, and ideally those reasons that we give will have some external validity, right? And in mathematics, that external validity is absolute, as it's been proven through measuring and different formal processes many times. That, for example, AD and AD are congruent, of course. I mean, that's obvious, right? But at some point through history, this was up to question, right? That 1 equals 1 was up to interpretation. And so only through the rigorous, painstaking works of people through history did we come to the point where we can just take some things at face value. And so then it is likely that today, although we aren't working from this similar level, we're not working from such a low level where we have to really prove that something is equal to itself. There are assumptions that we should prove, and that only through proving them, through repetition, will the culture and will the people learn to accept things as true or false, right? And so this process, once again, is irreplaceable, and it has a lot of value, not just in the maths and sciences, but in the world in general, but especially in the sciences. We'll come across this type of thing many times. All right, next we've got triangle BAD. So this triangle here is congruent to CDA through side angle side. We've got this side here, right? We've got this side, obviously. And then we've got these two angles. We've got this angle and this angle. BAD, CDA. So we've got two sides and the angle between them. And we know from, again, the life's work of many people hundreds and hundreds of years ago that we can just take that at face value. We know that's true. And so next up, angle CAD. CAD is equal or congruent to BDA. And that's because corresponding parts of congruent triangles are congruent, CPCTC. And once again, part of learning is knowing what people did before and having some respect for that. So paying a little bit of respect by spending time working on these types of things is a way of humbling ourselves before our humanity, before the legacy of people who came before us who spent their lives on what were certainly trivial and arbitrary and silly things to many people back then. But in fact had a value such that what seems like unimportant or irrelevant things even today is actually related to all of our favorite things, whether it's computers or video games or architecture or whatever. Simple things definitely expound into great things through practice and repetition. Next up, we've got AE and ED, of course. It's an isosceles triangle. But why? If two angles of a triangle, okay, so we're working kind of backwards. We know that if we start with an isosceles triangle and these two sides are the same, then we know the base angles are the same, but we can also work the other way. If the base angles are the same, then we know the sides are the same. And so finally, we know that AED is isosceles because it has two congruent sides, right? We know that the base angles are the same. We know that these two sides meet at the vertex, and if these angles are the same, then the sides opposite them must be the same also, and then they share a base. So it's isosceles with these two sides congruent, these two base angles congruent. An isosceles triangle has two congruent sides. Right, so once again, formal proofs can be they can take up a lot of time. It's some writing, which is sort of counterintuitive to what a lot of people are used to with math. But as we work up the hierarchy and into more complex things using sciences, we'll find a lot of sciences are kind of based in math, or they play back and forth. There's an interconnectivity where they're largely inseparable. And so this type of formological reasoning alongside some mathematical reasoning, and then expressing and representing this type of thinking in some sort of formal structure, like in this case the two-column proof, has a lot of value, and we'll see it's got economic and financial value later in life if we learn to use these things to have careers, obviously. And so this is a base level, but then we can build upon that knowledge and even gain wisdom over time. By subjecting ourselves to what's a little bit painful, it only makes us stronger in the end, right? And ideally, we can then also train our minds to think logically and to have reasons that formulate our opinions, and this can become kind of a feedback loop where our opinions even will become more based in and grounded in reality. Okay? So geometric proofs are an example of logical and formalized thinking where we're giving reasons for our statements leading to a conclusion. And by representing them all in this kind of table chart here, we can show other people, and they can, independent of us, come to the same conclusions. Rather than just jumping to the conclusion, we can explain each step of the way such that people don't have to have any faith in us. They can just have an understanding of reality as it is by our explanation. Okay? Thank you.